As I said, I'm Curtis Ballard with Hewlett-Packard Enterprise, and we got Austin Bolen from Dell EMC here today, and we wanted to get in front of you and tell you about an effort that we've been working on cooperatively, along with Joe Cowan from Hewlett-Packard Enterprise, who did a lot of the work on this but isn't able to be here with you today. So we're talking about a aspect of NVMe that you may be wondering, why do I care? PCIe hot plug and error handling for NVMe drives. I think I can see a few eyes glazing over already, but trust me, we all care, and hopefully we'll explain to you why you care and some of the ways you can think about participating. So quick overview of what we're going to talk about. I'm going to set up some of the importance of the hot plug and error handling for NVMe, some of the challenges we have with what we've got today, and then Austin's going to get up and talk about what we're working on for the solutions, and hopefully we'll have time for some questions. So diving into it, why is the hot plug and error handling for NVMe important? Well, it all comes down to a little thing that we call RASM. I've worked with a number of companies, and they've all had some sort of a concept similar to this. If you're not familiar with RASM, this particular acronym stands for reliability, availability, serviceability, and manageability. And for enterprise class systems, which Hewlett-Packard sells a few of, this is a very important feature for our customers. It's one of the primary discussions we have with some of our customers. And there's some quotes here from a document by Intel, and we would agree with these statements. One of them there is that adding or improving on RASM reduces total cost of ownership. Now, if we flip that, the important thing for us today is that decreasing RASM increases TCO. And today, to deliver NVMe drives, we decrease RASM, we increase TCO, and it's a barrier to our being able to sell NVMe drives to our customers. There's another point on this quote there that the average cost of unplanned outage runs into the hundreds of thousands of dollars in these big systems. Some of our customers that are happy to yell in the case of unplanned outages will say that number's too small. So it's a big deal when we have any problems. So we've got customer requirements that they want support for surprise async and hot plug. They don't want any sort of prepare to remove. You would be amazed at how difficult it is to go into a customer that's been using your systems for a lot of years and tell them, oh, now your service process has to be more complex because we're adding a new capability or new part. Sometimes those service processes can't be changed. We need to get to parity with SAS or SATA or better than what they have today. And that means we have to be able to handle the hot plug events on the PCIe bus. And more than that, we want to be able to handle all of the events on the PCIe bus, whether they're due to surprise async removal or not. When you increase the number of PCIe buses, you increase the number of devices on your PCIe bus, and that PCIe bus is able to inject errors that can cause your system to crash, you just reduce your TCO. And we're trying to avoid that. So reliability, I think everybody here wants to build a reliable system. That's part of why we're here. But despite all of our attempts to build reliable systems, there are going to be some small failure rates, and when you get into large-scale systems, that multiplies, and your failure rate will go up. And some of our customers run these things clear through end of life and beyond, and NAND will wear out. There will be failures of these systems. We will have to replace drives, and our customers expect to do that while the system's up and running. So we have to have hot plug. Manageability. Manageability talks about the ability to detect faults, the ability to inventory your system. All of these things are things that affect how things work over the PCIe bus. And so this touches on that as well. Simple things like inserting a new drive, how fast you can detect that and get it configured, or removing a drive if the system detects that appropriately. Serviceability, this is the really big one. The async and hot plug really is required for serviceability that's equivalent with SAS and SATA drives. I've heard people talk about we need to move off of SAS and SATA onto all NVMe, but we've got to bring NVMe up to the same level of serviceability to do that. And if we have async or surprise removal support, that removes some of the requirements that we have to put on our customers today. There's orderly removal processes that have to be followed. And some of the customers, a technician that is supposed to be repairing or replacing drives doesn't have the system access to do software processes for orderly removal. So then you end up putting on things like expensive hardware buttons or switches or interlocks, and it drives up the cost of the solution. And then availability. If we have hot plug, then that can increase the availability by avoiding costly downtime of the systems. We don't want the system down to replace failed drives, and we don't want the system to have to be down to do any provisioning storage. So what are the challenges? Why is hot plug so hard? We're making these drives. We just put features in them so they can be hot plugged, right? Well, it's not that easy. You know, some of you've seen this type of a figure before. There's the elephant analogy that depending on where you're looking at the elephant, you see different parts. For the NVMe ecosystem, it's a big ecosystem. There are a lot of different parts, and some of us in this room have the ability to change maybe 2 or 3 of these parts, but we can't change the whole stack. You have to have changes in the drive to support hot plug. You have to have changes in the platform, and that's all the way through the platform. The backpanel management controller, the firmware, the hardware, all have to have tweaks or changes. The PCIe report and switch has to have hardware and firmware changes in it. Operating systems have to support features, and it's clear into the NVMe driver, the PCIe driver, the ACPI driver, and even sometimes it goes clear up into the applications. So when everybody's looking at their own piece, we don't get anywhere, or we don't get the solution that's really as robust as we'd like. Some of what we're trying to do today has been tackled previously, but we didn't have that full ecosystem view, and it's not quite where we need it to be. So why do we have this problem? I've had people ask me, we've been doing storage devices for a lot of years. Why is the NVMe drive harder to deal with hot plug or async removal than SAS and SATA was? It kind of comes down to this diagram we put together here for you, that these systems will have a hot plug barrier that is the level below which you can hot plug things, pull power supplies in and out. They're below that hot plug barrier. In the case of SAS and SATA, we had the drives outside the hot plug barrier. We had a SAS and SATA controller hooked up to the microprocessor inside that hot plug barrier. Those are the SAS and SATA drivers that talk to the operating system, bound to a hardware controller that was inside the hot plug barrier that didn't get taken out, and they did a protocol conversion. So we had protocol conversion happening, providing a level of isolation. We had hardware physical layer conversion happening, providing a layer of isolation. So it was relatively easy in a fairly constrained set of pieces to design a way that major errors on the bus, and the SAS bus or the SATA bus, didn't turn into major errors on the PCIe bus. They'd turn into a error report on the PCIe bus using PCIe compliant protocols, but they wouldn't be an error on the PCIe bus. We've changed that architecture. Now we have an NVMe drive plugged straight to the PCIe bus. The NVMe controller, in many respects, has moved down into the drive. So now the controller and the drive are down inside the hot plug. They don't have that level of isolation that we had before. So have we seen this before? Haven't we worked on this before? If you've messed with PCIe very long, you've seen hot plug for years. I've worked on systems where PCIe hot plug has been talked about for at least 10 or 15 years, and I'm sure it's been a lot longer than that. So there's been things done for a long time. There's one model called the standard hot plug controller model. We abbreviate it as SHPC. That model has been around for a very long time, was around with PCIe, PCIX, and some early PCIe. It's a complex model, and it required some additional controllers or some additional hardware with some power controllers, etc. So It could work, but it required special processes and was expensive. So another tact was taken called the hot plug surprise. Hot plug surprise has been in for a fair number of years. It hasn't really taken off a lot in systems until recently. The emergence of PCIe storage and Thunderbolt was where we started to see people implementing support for hot plug surprise. Now we've got NVMe attached into those buses. Hot plug surprise is a little bit more interesting. All of those types of storage systems, Thunderbolt and NVMe, and anything else that plugs into that PCIe bus can benefit from what we're doing for hot plug here. And it supported some hot plug insert remove with specific restrictions. But after we did all of that, we got the SHPC. It was expensive, complex, came up with hot plug surprise, a little bit easier. We still have difficulty. There's still system crashes that are possible. As we've used HPS, we've learned that it is extremely difficult to close all the corner cases. There are still some errors possible, even when orderly removal process is followed. And some of the orderly removal and the way the process works, it hides errors that happen on the PCIe bus, which can make the software have even more difficulty handling some of these errors. It synthesizes all one's data during errors. That isn't always handled well. And there wasn't really a strict model written for how the whole system interacted, what the software was expected to be able to do. And so we ended up with, there's cases where you can have crashes and deadlocks. A lot of people have spent a lot of time working on this, and we've heard over and over again, don't worry, it's fixed, it works. And then you deploy it in volume, and it crashes. So there's a few other issues. Timely detection, removal, and insert has been hard. There's some mechanical issues with insert and remove. You slide a drive in too slowly, the system can detect that the drive's there before all the signal lines are connected, and things don't work out right. And then anytime we find a problem, we find out that there's multiple components that have to be changed that are outside of the scope of our ability to change anything in any timely manner. So it ends up being a multi-year process to fix any issues we find. So those just weren't complex enough or weren't robust enough for the complex use cases that we're getting into now as NVMe is growing up. So HPE and Dell teamed up and worked with some other companies to try and come up with some solutions to that. I'll let Austin talk to you about what we're doing.
All right, thank you, Curtis. So my name is Austin Bolen, and I was going to pick up from there and start talking about some of the solutions that we came up with to solve these NVMe hot plug and air handling challenges that Curtis covered. So the first thing I'll talk about is some of the key design tenets that we came up with for the solution. The main thing we wanted to do was to create a hot plug and air handling and recovery toolbox, something that had a lot of flexibility in solutions. If you look at the different NVMe solutions out there, they're so diverse that we knew we wouldn't be able to come with a one-size-fits-all kind of canned solution. For instance, there's just so many different systems and form factors and operating systems, and each one of them has their own unique requirements, and these requirements can change with new products. So we had to have something that was flexible enough to adapt to all of those. We also needed something that was flexible enough to extend beyond NVMe. We were obviously focused on NVMe, but we want this to be able to be used for all types of PCIe devices, especially ones that need hot plug, like Curtis mentioned, like the Thunderbolt docking solutions and so forth. Hot plug is so complex, it was really difficult to kind of foresee all the issues up front. What we found is that, issues pop up. You can have silicon defects. You can have issues in the platform hardware or mechanicals. You can have OS bugs and just on and on and on. And so we need something that was flexible enough to be able to adapt and address those issues as they pop up. Another thing we did was we kind of canvassed the industry. We talked to many different people to see what their pain points were, what kind of problems they were solving. And we set out to make sure that we had the tools in place to address as many of those known issues as possible. We also wanted to make sure that we leveraged the lessons learned from some of the existing solutions out there in the industry. So for hot plug, we looked at SAS and SATA. We wanted to achieve parity with those models, obviously. That meant eliminating the need for orderly insertion and removal. For the error recovery, we leveraged heavily from existing proprietary mechanisms that have been used in the enterprise for many years. We also wanted to come up with a phased approach. I mean, there's, the problem space is so large and there's so many moving parts. We knew that we wouldn't be able to solve everything all in one shot. So it was really important that we had something that we could, roll out in phases with incremental improvements. We also wanted this to be able to apply to all types of PCIe errors. We were obviously very focused on making sure that we could handle and recover from hot plug related errors, but we also wanted to be able to handle and recover non-hot plug related errors with the same mechanisms that we were defining. The final key design tenet that we had here was that we needed something that really would allow for a fast time to market. Whenever we have to go and design new systems or new form factors or fix defects. And the way that we did this was we added in hooks to allow the system firmware to get involved on hot plug and error handling events. Typically from the platform side, we can churn out the firmware fairly quickly. And this, minimizes the need to have to change the operating system or the silicon to address these types of things, both of which typically would have a much longer time to market. So we knew for this to be successful, we'd have to get a broad industry alignment. So we spent the time to talk to a bunch of different OEMs and also the operating system vendors, and then also to make sure we could handle the OS native controlled case with no firmware and things like that. We also spent a lot of time doing design reviews with the root port vendors and switch vendors to make sure that what we were defining was going to be implementable. We also knew that we wanted to have a standards-based solution. Since there's so many players, we needed that for better interoperability, and of course all the other benefits that come with the standardized solution. And as we saw on the slide Curtis presented with the parable of the blind man and the elephant, people have been looking at their own piece of the puzzle and asked the question, well, who's looking at that overall solution? And so the companies listed here, HPE, Dell EMC, and Intel, we collaborated and we worked together to design that overall solution and then led the effort to drive it into the standards bodies listed here. And I'd especially like to recognize and thank Joe Cowan from HPE and Mahesh Natu from Intel. They both provided a lot of assistance in defining this and getting it through the standards. They both have a wealth of knowledge in this area, so we were very fortunate to get their expertise. So on the bottom table here, we have a list of the ECNs we developed. All of these are ratified now, so they're complete, they're ready to go. The three main ones that we defined were the system firmware intermediary, containment error recovery, and then some additions to the hot plug extensions in the ACPI spec. And I'll talk about each of those a little more in the coming slides. So as Curtis mentioned, we have some issues with the current hot plug surprise model. So what we're trying to do is we're trying to transition the industry over to a new era, which we're calling containment error recovery, or CER. With this, there's a change in terminology in the PCIe specs. They're replacing the term surprise with async when referring to unannounced hot plug events, so just something to be aware of. CER is a software and firmware model that's defined in the PCI Express base spec, and it can be used to recover from many different types of errors. It's built on top of downstream port containment, which is, or DPC, which is an existing feature defined in the PCIe base spec, and it's implemented in root port and switch downstream port silicon. There's two different modes for CER. One is the native OS controlled, if you don't want the firmware involved. So in that case, the OS would be solely responsible for handling all the errors on its own. And then there's a firmware first model where the system firmware and OS can work together to recover errors. Now on the right-hand side here, we have an example system with some NVMe drives connected, one directly to the root port and a couple connected to switch downstream ports. The system will enable DPC in each of these ports to detect and contain any errors that occur below them. And so the way that this will work is that if you have an error or some kind of async remove event, that will get detected in the port above it. The DPC logic in the port will then contain the error by forcing and keeping the link down so no other data can flow. That way the error is contained. The port will then notify the firmware or the host operating system, depending on which mode you're running in. The firmware and or host OS entities will then attempt to recover from the error. And then finally, the host will release DPC, and it'll restart the device if it's still present and recovered. So next we have the SFI era, or System Firmware Intermediary. This is not something that's going to replace CER, but rather it augments it. SFI adds a layer of isolation between NVMe drives and the host OS, but it only does this for hot plug, so the data path remains as it is today. It doesn't interfere with that. Like DPC, SFI is hardware that's implemented in root ports and switch downstream ports. It provides the option to invoke system firmware on hot plug and error handling events. And this can be particularly useful if you need to do some kind of system-specific initialization of a hot inserted devices that's really complex, like some of the complex security or authentication tasks. So the next thing we did was add in support for, or actually add on to existing mechanism, which is called HPX, which is a part of the ACPI specifications. ACPI defines a software and firmware interface between the system firmware and the OSs, and this existing mechanism allowed the system firmware to provide the OS with instructions on how to program the config space of devices that were hot inserted or reset at runtime. But it was done in such a way that the registers were hard-coded, and so every time the PCIe specs added a new register, you would have to then go and update the ACPI spec and spin all the OSs, and it just took forever. And so what we did was we augmented that and did it in a more generic way that doesn't require changing the ACPI spec or updating the OSs when new registers are defined. It also adds a simple if-then-else grammar that allows conditionally applying changes. And on the right, we have some example pseudocode that shows how you would use that grammar to, for instance, program the completion timeout value on a device based on the ranges that it supported. So for next steps and how to get involved, as I mentioned, the standards work is complete. It's all ratified and ready to go. We've already started on implementation phase. For the PCIe root ports and switches, there are some out there that already support downstream port containment, and we're trying to get that added into the remaining ones as well. Likewise, we're trying to get SFI support added into the root ports and switches as soon as possible. For the OSs and OEMs, we're looking to have support for async remove in the old HPS model as a stopgap until we can get CER everywhere. Again, it's part of this phased approach. In parallel, we're starting to push to get the containment error recovery model implemented everywhere. The hardware is already available. The OEMs are developing the firmware. There's also an open source effort already underway with patches submitted to the Linux kernel. And then finally, for the connectors and form factors, if you're designing anything that needs to be hot pluggable, we're asking that those be designed up front for async hot plug. And there's a list of considerations here to help avoid some of the issues that we've seen with previous connectors and form factors. And with that, thank you. We'll open up for questions.
All right, we've got a couple of questions Notably, Christoph's hand is not up. All right, we'll start with you, and then we'll go back and.
All right. So, as you're probably aware, one of our most popular form factors, M.2, don't go there. What do you want to do? I haven't heard any call to action on that.
And you go, that was just, I briefly covered the last slide. We had a list of actions.
Yeah, I saw it, but actually we already have it for, it's already there for chem, it's already there for small form factor, it's there for EDSFF. But if you look at where an awful lot of stuff ships, it's M.2. And it looks that way for multiple years.
So that's why we put in the call to action, like all new connectors and form factors got to address that. Absolutely. And M.2 is one of the reasons.
That's not new.
Yeah. Exactly, yeah.
Thank you. If you do the DPC and EDPC right in your system, why do we need SFI? What is the real value SFI adds?
I'm sorry, could you repeat the question?
In your, if you go back to your slide where you were talking about the next steps, when you said DPC and EDPC is done right. No, the next. Yeah, this one, yeah. So we are going to, let's say we are doing a DPC and EDPC. So if you're doing that, why do we need SFI?
DPC and EDPC are more geared towards error handling and recovery. So whenever a device has an error or you removed a device, SFI is more useful for hot insertion. So if you hot insert a device, today, for instance, if you boot up a system with an NVMe device installed, the firmware can do platform-specific things to it, and then you hand over control to the OS. When you hot insert that device in the OS today, the OS gets notified immediately, and there's no opportunity to do any platform-specific things to it, and that's what SFI gives you.
But that's only... Yeah, that's a bit... Sorry?
Well, it's going to be in the same state as the BIOS gives it when you boot the OS through it, so in that case, it's no different. What will happen is if there are platform-specific issues, when you boot the system and the firmware goes first, those issues will be taken care of, and when you hot plug it in the OS, it won't work right.
So SFI is only in PCIe switch, or is it also in the CPU subsystem?
It's in the PCIe root ports and the switch downstream ports, yes. Oh, what was that?
I'm coming. Don't take that down.
Could it be configurable so that to make could it be configurable so that would satisfy some of the OS vendors who feel like it's best for the firmware to stay out of the platform firmware to stay out of the picture as much as possible versus systems that maybe are running older OSs that are not reacting gracefully and will crash.
Yeah, absolutely. So,
is that built in?
Yeah, so like I mentioned, there is a native OS controlled mode.
Okay.
And so if you have customers too that want to run in a native OS controlled mode, then they can do that. They can turn off all the firmware stuff and they can run, just how it's being asked with just the OS involved.
So that sounds great. You have a choice, which we don't have a choice.
Yeah, we have a
today.
choice. Our customers prefer firmware first. I know some of the OS guys don't, but we'll let the customer decide.
Yeah, and there's some configurations where we have drives that require specific setups for the operating system to run successfully. And if we can't get in there and do that specific setup, the operating system can't use the drive. So the firmware first can be pretty important in certain configurations. We try and minimize it, but it does give some flexibility. And it helps some of the drive vendors because there's times where a drive vendor can deliver one SKU instead of two potentially if we can set up some things right at power up and hand it off in the right config.